Hello, we are back now to dive in training using backpropagation algorithm, sometimes called gradient descent as well. So now, so just a recap, we were talking before how the training process work, and you can summary that process in two main steps, which is feed forward, pass the input, do a feed forward through the layers, and get the final prediction, and based on this prediction we calculate the loss based seeing how far the output it is from the expected value, so in this case label. And with this calculation we can see with the loss we can then update the weights, going backwards and navigating through the layers, and update the weights for each layer. Okay, just what I was just talking was about this process here, right? So feed forward, check the error, and based on the error that you get on the final output, we go back and update the weights across the layers. Okay, so now time to look at the process of feed forward first, and let's dive in. Feed forward, it is basically we receive our input, we transform this array input into matrix, because you're gonna learn that machine learning is basically a sequence of matrix multiplication and basically matrix operations. And so for handle those matrix multiplication, we have this class where we provide some basic matrix operations, and here you would be able to see how things really work, how multiplication works. So you'll be able to look at the code. I have had some comments around. So for example, you'll be able to multiply a matrix with a number or with a matrix, and if it is just a number, that's how things works. And when it is two matrix, you can see how a matrix multiplication works. The same, you can see how to calculate some product with matrix, when you basically multiplying columns with rows. You can see how that thing happens here as well. So very transparent, and you can look at the code and trying to you are gonna be understanding what is behind the hood very easy. Copy, I have transpose, where transpose it's basically transposing let's say the shape of the matrix, and essentially it's just changing column by the rows. So you can see here E became J and I become J as well. So it's just a simple change of rows and columns. That's it is transposed when you see that later on the part of the network. Somehow to add apply addition on matrices. So again, you can see how it is done. Basically loop through rows and columns and perform the addition. We have also the addition with this scalar number. So you can see here you can pass a matrix or a number, and if it is just a number, it's just a simple addition. We apply a function to each element as well, when this will be used for the activation function. So basically a loop over, and again just passing as a param to our function. Very simple. And we have some randomized way to generate matrices that will be used for our weights and bias, and we will be able to create matrix from arrays and pass to array from matrix. It's basically this operation that will be required for our neural network. Going back to our feed forward step, first thing it is matrix, transform our input into matrix, right? And then we loop over each layer again. Layers, it is here, we are going to each layer. So we are on the input layer, and then hidden layer, then next hidden layer. In our case, only one hidden layer, and then output layer. Let's keep going. So when you are in the layer, we process the feed forward inside the layer. So on this step here, you're gonna need to do the feed forward on this guy. So what is involved on this feed forward? Basically, in our artificial neural network, learning occurs in the following fashion. So each neurons, also called as a node, receive one or more inputs from external source of the other neurons. Next, basically, you get the input. Each input is multiplied by the weight to indicate the input's relative importance. So then this, it is here. So basically we have, if it is input, you don't do anything, because input is just the input. You don't need to perform any let's say learning on the input layer. So do multiplication, then you do the addition to the using the bias, which it is happening here, and then we apply the activation function to the final output before set the output. Let's understand what it's weights on this context, right? So why you need weights? So weights here, it's trying to represent the strengthening of the connection between neurons. So it's basically how learning occurs on the biological brain, and we try to reproduce this characteristic in the artificial brain as well, and that is through weights. So with the weighted inputs, the network can increase or decrease the strength of the connection between each neuron in the layer and the neuron in the next layer. So what it's describing here, it is that weights will represent the strength between this neuron and the next neuron, and so on and so on and so forth. So every neuron is linked to each neurons. Basically, weights are the coefficients of the equation which you are trying to resolve during the training phase. So this is the coefficient of our equation. So we are trying to get the optimal weights for our layer. That's what we are trying to achieve through this training process. Bias, we are going to use bias as well, and bias, it's basically it's basically trying to add some flexibility and basically improve the generalization. What that means is, if we don't have a generalization, we will not be able to predict images that was not used during the training. So that's a bias, and the activation function play a big role on this step. And we can weights and bias, we can see how a little bit this in action on another project that we'll be looking later, and it is a self-driving car, and we can see here the arrows. It is the weights, and it is expressed how strong it is this this neuron to the other neuron actually, and you can see this strength by the strength of the arrow. So and if it is red, it will be on a negative way basically. So depending on the inputs, we will be seeing how the strength between neurons and across different layers. So we are going to be exploring this project more in the future. And the same we can see for the bias. So the bias here, it is the circle around our circle. So this here you can see that this is more strong, this is less strong, and this is just the variance that we are adding here. And yeah, this project is very interesting. We are going to be looking at it later. Let's go back to our digital recognition. So where we were, it is looking at the feed forward inside the layer itself, right? And you can see that it's just three steps that happen during this process. It is the multiplication of the input and addition of the bias, and plus applying the activation function, which we are going to be looking in more detail later. Okay, this is basically what is feedforward is, and that's all. Based on this, we will get some prediction based on the input. Next step that we are going to see is the calculation of the loss, right? So we got the output, and now you need to see how far we are from the expected output. And the calculation goes first in a reverse order. We have in a reverse order on the layers. And why is on a reverse order? It is because we are here and you want to go back, right? So that's why back propagation. And some we skip when it is output, and then we start to calculate the loss for each one. And the calculation of the loss is basically very simple. So on the output, for example, we are just doing a multiplication, matrix multiplication. Remember that I said that it's full of matrix operations. Neural network, it is basically deep learning. It is basically a matrix operation applied in different ways. So here, basically, this loss calculation just use a simple multiplication plus addition against the expected value, and then that's on the first layer, right? But the subsequent layer, not output layer, I'd say, it is a bit different. We do some transpose that I already explained what the transpose, and the transpose it's required because now we are doing backward, so we need to kind of turn the weights to be able to do this operation. And then we just multiply this transpose weight with the error that we got before. And this is basically that. So each you have different error loss calculation. So this is one way, and you don't need to get much into the details here because this will depend of which error loss you are using, error loss calculation. And this is basically you're gonna just be using different one. You're never going to need to implement things, so you just get already those ready to use. You just did here. We are just showing what it is under the hood on a very simple way, right? But I don't need to bother with why adding, why multiplying. So this is it's a result of years of research and a lot of people putting a lot of effort to come up with the most optimal way. So don't bother with this, but it's important to know what it's under the hood. So then when you finish the calculate of the loss, we need to update our weights, right? And the update of the weights, again, you're going on a reverse way, and you just first calculate the gradient, and the calculation of the gradient it is here. And what is gradient? It's basically tell us the direction we need to go to minimize the loss by helping to adjust the weights and the bias. So this is one more step that would help us to improve the weights, telling which direction we should be going when you are updating our weights. So to exemplify this, so another important thing is how big the steps the gradient will be. So we take the direction, and we say also define how big is the step we are going to go towards that direction. And learning rate would play a big role on this step. So that's why it's one parameter that you need to define, and one parameter that you need to try. Let's say that's a part of our machine learning engineer as well, come up with a good learning rate. Let me give a small example, more visual one, what I'm talking. So here, back to my notebook for my CNN course, you can see on the derivative in gradient how it's used. When you talk about direction, so we are saying that if I'm in the A position and I need to get to this position 0 here, which it is the loss, low loss, zero loss, I need to know which direction should be, to the left or should we go to the right. So if I'm in the A position here, I need to go to the left, but if I'm in the B position, I need to go to the right, and I need to know what's the steps I'm gonna take. How big is the step? If it is too small the step, it's gonna take too long to go here to the optimal position, but if I take too big, I can pass the position and never get to the right, to the most optimal location. And another example here, it is the learning rate. It's what control how big is the step, as I mentioned already. So if it is too small, it will take too long to get to the position, but if I get too big, I'll be going too much and overshooting and never get to the optimal position that you want to get. So that's learning rate, that's derivative, and that's how we code those things. Very interesting, isn't it? Like it's mind-blowing to see how things that looks so complicated, it's pretty simple now that we know the math behind, right? So after we have the gradient, as I mentioned, that will be used to update our weights, and here you can see our weights being adding, and this is basically a result of the gradient plus the output of the previous layer. And here you can see that can be negative or positive. That's gonna be defining what it is the direction, basically. And the same, we use just the gradient to our biases, and that's the full training logic of our neural networks in general. And I think with that we got to the end. So we dived through the operations of it's involved during the training. I hope you guys have enjoyed this journey, and please have a look on the code and trying to digest by yourself, and now that you know those steps. So I have added a lot of comments to help you when you are checking the code, and if you have any question, leave the comments and I will try to answer all of them. Thank you very much. See you in the next lecture.